Now that we've done law of sines and law of cosines, the next step is to work on vectors. So this is probably going to be 2 videos because there's a lot of material in here. This is the first time I think you're seeing vectors, and then in the next section, we'll do a little bit with the dot product. So the beginning of this is an introduction, and what is a vector? Well, first of all, a vector has magnitude and direction. So it looks a lot like a ray. In other words, if you remember from your high school geometry days, you had these things that started here at a point and then went on forever in one direction. Well, that's a ray. A vector, oddly enough, when we draw it, looks almost identical. The difference is that the vector is exactly what you see. In other words, it starts here at the tail and it ends here at the head, and it goes exactly that much in that direction. So vectors can represent all kinds of things. If you're pulling on something to try to make it move, like you're moving a couch across the floor or something like that, then the vector might represent forces. It might represent the direction that that thing is moving. If you're hiking somewhere or you're in a boat and you're navigating somewhere, from wherever your origin point is, you might be going north, south, east, west, a certain number of degrees in a certain direction for a certain amount of time. And that in that case, the vectors could represent distance or they could represent your speed, right? If you're traveling 30 miles an hour to the southeast, then there's actually a certain amount that you're going east and a certain amount that you're going south, and you can break those apart into their components. So I mentioned about the fact that it looks like a ray, but it's not really. What can it represent? The notation that we use for a vector is twofold. We could label it with the bold letter V, and when you see it in the textbook, oftentimes that's what they'll do because they have those printing capabilities. When I'm drawing here on a whiteboard, or if I'm drawing on a classroom board, or if you're drawing with a pencil, it's very hard to make a bold V that differentiates itself from a non-bold V. So in that case, generally what I'll do is I'll put an arrow on top of it to indicate that it's a vector. It's not just a variable of some sort, but it has other meanings besides a variable. It represents a vector. So when the vector starts at the origin, you can write it like that with those little brackets. So if I had the vector 4, -2, what that's saying is I'm starting at the origin, and look to see where it ends. It ends 4 units to the right and 2 units down from its starting point. So that's its head. Its tail is over here. Okay, so that is the vector. It starts at the origin, and it goes that much in that direction. And so I can write that vector as 4, -2, meaning it's not an ordered pair, right? It's not just the point 4, -2 over here. It's the vector that starts at the origin and goes to that point. So what is the notation? You can find out how long the vector is, the magnitude of the vector, and I've seen it written with just 1 bar before, right? That's also another way of representing the magnitude of the vector. So suppose I wanted the magnitude of this vector 4, -2. Well, if nobody gave you a specific formula for it, and you had to figure it out, you might go, well, look, I can draw a line segment here and a line segment here. They make right angles. It's 4 across this way. It's 2 across that way. Well, I know what the Pythagorean theorem is. I can say c squared equals 4 squared plus 2 squared, and that's 16 plus 4, so c squared is 20. Take the square root. We're only going to use positives here because it's a length. And 2 square root of 5 is how the radical simplifies. So it really is the Pythagorean theorem. What notation do we use, either with the double bars or the single bars? And down the bottom is the formula. The magnitude of a vector is the square root of a squared plus b squared. Someday you get into 3-dimensional vectors. Surprisingly enough, if you add a 3rd dimension, it's the square root of a squared plus b squared plus c squared. Sometimes you also see vectors with their endpoints as notation. So I could have written that vector before that I had up there 4, -2 by calling point P the origin and point Q the endpoint over here, in which case instead of calling it vector V, I might call it vector PQ. Okay, that notation gets a little bit goofy because then you go, well, is that a ray or is that a vector? But we can label it that way. And then if you want the magnitude of that vector, then you would look for the magnitude of PQ, like so. So, question. Draw the vector 3, -1, find its magnitude. So let's do it. Where's 3, -1? Well, it's in the same spot almost as the last example I did. 3, -1 is 3 to the right and 1 down, so that's my ending point. Written like that, the vector goes from the origin to that ending point. So what is its magnitude? I could set it up with a Pythagorean theorem, right? Here's 3, here's 1. Or I could just use that formula, that if this is a and b, then the magnitude of that vector is the square root of a squared plus b squared. So it's the square root of 3 squared plus negative 1 squared. Again, remember, when you square a negative, you get a positive, so 9 plus 1 is 10. The magnitude of that vector, which I'll call vector v, the magnitude of that vector is the square root of 10 units. It's linear. I didn't give you any units for this. Oftentimes, there won't be units unless it's an application problem. So we'll just leave the magnitude as the square root of 10. All right, with this vector, you also notice that besides having a magnitude, it's also got some sort of a direction. And we'll look at a couple of different ways throughout the section to represent direction, but one of them is with a direction angle. So the direction angle is the smallest non-negative angle that the vector makes with the x-axis. So if I consider that angle there, I'm going to represent it as a positive angle, even though it's below the axis. That would be the direction angle. And so if I want the measure of that angle, I can get it using tangent, because that's my direction angle. That's 3, that's 1. That angle is the inverse tangent of opposite over adjacent, and then I would just throw it on my calculator and find out what that direction angle is. So we have a name for it. We usually call it the standard representation for a vector. Smallest non-negative angle that the vector makes with the x-axis. And there are other angles that we will use to measure these things, but if you see the standard representation or you see the direction angle, that's what it's referring to. All right, I threw the words heads and tails in before. Here's a more formal definition. The side with the arrow is the head. The initial point is the tail, right? Where do things start? They start at the tail, they end at the head. If you've got something that is not at the origin, so suppose you have a vector out here, and this is the ordered pair. And again, we're going to have to be careful of the difference between ordered pairs and vectors, because they can look very similar in notation. So suppose this is the ordered pair 2, -1, and this here is the ordered pair 6, 3. Now, neither of these are at the origin, but yet I can take that vector and I can move it back to the origin by doing head minus tail. So remember, that's the head, that's the tail. And so basically I want to know how far did it move along the x's, how far did it move along the y's. So I would do the difference of 6 and 2, right? So 6 minus 2, that's my first coordinate. 3 minus a -1, that's my second coordinate. So 6 minus 2 is 4. 3 minus a -1 is also 4. That's the head minus tail rule. So if you look at the x's, it went from 2 to 6. So what did it do? It went 4 in the positive x direction. It went from -1 to 3. So it went 4 in the positive y direction. So I can use that head minus tail rule and get it back to the origin. So this is the formal definition of head minus tail. It's got initial point x1, y1, terminal point x2, y2. So the new vector is the difference of the x's, the difference in the y's. Again, starting at the head, subtracting the tail point. And when I do that, it tells me how far it went from the tail back to the head. So you notice this one moved 4 units to the right and 4 units up. So I'm hoping to help you make heads and tails of this. All right, so here's an example. It says, suppose u is a vector with its given endpoints, find its magnitude, find the direction angle. So where is -3, 5? -3, 5 is up here somewhere. Where's 112? Well, it's off my screen the way I drew it. Here, I'll stick it up on the top. Not drawn to scale, but here's -3, 5. Up at the top there would be 112. Now, I could almost look at this and go, well, from -3 to +1, it went 4 units to the right. From +5 to +12, it went 7 units up. There's my head minus tail. I could also do it with the formula, right? So the formula is take 1 minus a -3 as my first coordinate, take 12 minus 5 as my second coordinate. So 1 minus a -3 is 4. 12 minus 5 is 7. All right, same answer I got. What I'm saying is that if I had taken this vector here, I could bring it down to the origin as the vector 4, 7. Why would I want to do that? Well, because I can get some information about not only its magnitude more easily, but I can get information about the direction angle. So if I want the direction angle, I create a right triangle here. We said it went 4 in this direction and 7 in that direction. That's the direction angle right there. So based on that, I'm going to use tangent. The tan of the angle is opposite over adjacent, which means the angle is the inverse tangent of 7/4. So grab a calculator, put it in degree mode, because generally we measure these things in degrees. Take the inverse tangent of 7/4, and I get 60.26 degrees. And the other thing I could find if I wanted to was I could find the magnitude. Okay? So the magnitude of the vector would be the square root of 4 squared plus 7 squared. So I get the square root of 16 plus 49 square root of 65. Right? So that's the magnitude. So I have magnitude and I have direction because vectors have both magnitude and direction. All right, so all of these operations have been with one vector. Suppose I introduce a second vector and I want to add them together. So if you're trying to move, let's say, a couch across the floor, and you're pulling one way and somebody else is helping you and they're pulling another way, where does the couch go? So when we add two vectors together, we add them head to tail. So the arrow of one side has to hit the point on the other side. So if I add those two vectors together, what comes out of it is what we call the resultant. And so the resultant is the sum of those two vectors. And it really is as simple as adding the two x coordinates together, adding the two y coordinates together. And so in the picture that's down the bottom, I'm adding vector u to vector v. So if somebody's pulling this way and somebody else is pulling that way, where does the piece of furniture go and how far? This is the resultant. That vector that's in blue is u plus v. Notice that when they added the vectors u and v, they added the head of vector u to the tail of vector v. If they're not listed head to tail, we can move them so that they are head to tail, and then we can add those vectors together and get some idea as to what they do. This is sometimes also called the triangle rule, because you notice the vectors u and v, and the sum of those two vectors form a triangle. So let's try a couple of these. We'll do one, and then we got a second one down the bottom. Here's two vectors at the origin, 3, 5, and negative 7, 2. So 3, 5 goes 3 to the right and 5 up. All right, so I'm drawing a rough sketch. There's vector v. Vector u goes 7 to the left and 2 up. So there's vector u. Draw the vectors, draw the resultant vectors. Now you notice that the way they're drawn here, they're not drawn head to tail. They're actually drawn tail to tail. So what do I do in a case like that? Well, I have some options. I can either slide vector u up, or I could move vector v across. Either one will let me add them head to tail. So here, let's take vector u and put vector v at the end over here. And now I can add them head to tail. So the head of vector u and the tail of my new vector v match each other. So if you think of taking this vector v and sliding it all the way across till it gets to that point there, now I can add them together. So u plus v is 3 plus negative 7, that's the first component, and 5 plus 2 is the second component. So 3 minus 7 is negative 4. 5 plus 2 is 7. So but the resultant vector is negative 4, 7. Now where is that? Where is the vector negative 4, 7? It's 4 units to the left, and it's 7 units up. So it would make sense that this thing over here is my resultant vector. Meaning that if you pulled one way in vector v and somebody else pulled the other way on vector u, then where would the object move? It would move in the direction of that green. Because notice it's being pulled more to the left than it is to the right. And they're both pulling upward, so you add the upward components together, you balance out the left and right, and you find out where this object moves. So the resultant vector is negative 4, 7. It also asks for the direction of that vector. Well, where is negative 4, 7? Let's take a look at the angle that it makes with the x-axis. The vector moves 4 units this way. It moves 7 units that way. So theta is the inverse tangent of 7 over 4. And we actually get the same answer as before. But the answer that we get is this angle here. If we want the angle that it makes with the positive x-axis, we would subtract from 180 to find out how much it moves in the direction from the positive x-axis. All right, let's try the other example that I had put down the bottom, where a was negative 1, 7, and b was 2, negative 4. All right, let's take a look at what these vectors look like. So negative 1, 7 is 1 to the left and 7 up. So there's vector A. Vector V is 2 to the right and 4 down. That's a very wide angle on that vector. So I want the resultant of adding those two together. Well, again, because they're both drawn from the origin, they're really tail to tail. So now how do I make them head to tail? Well, I got to slide one of them. So I could just simply mechanically add these two things together, right? Vector A plus vector B is negative 1 plus 2. Well, 2 minus 1 is 1. 7 minus 4 is 3. So the resultant vector is going to go 1 to the right and 3 up. So 1 to the right, 3 up, is approximately there. So the resultant vector is in red over there. And then you could think about taking that vector B and sliding it up. And now that's the result of adding those two vectors together. So I can just do it with adding the x's and adding the y's. So if somebody's pulling one way and somebody's pulling the other way, what's the result of those forces? It moves it in the direction of the red vector. So 1 to the right and 3 up. So there's more, like vector A has more going up than B does pulling down. So the result is that it moves more up than it does down. And the same thing with the left and right. They're kind of balanced, but vector A moves 1 to the left, B moves 2 to the right, but net change, it moves 1 more to the right than it does to the left. All right, let's talk about equal vectors in the next video.